Hello everyone, I am Dr. Lakhvinder Kaur, Associate Professor at Rumta College of Engineering and Technology, Bhilai. Today I am going to explain a topic, overview of optical fiber communication. I hope to share some valuable insight that will benefit you all. So let's get started. These are the outline of presentation which we are going to discuss. Introduction of optical fiber communication, history and evolution, basic principles involved in optical fiber communication, structure of optical fiber, types of optical fibers, key components of optical fiber component system, applications, and followed by the conclusion. Introduction to optical fiber communication. Fiber optic communication is a method of transmitting information from one place to another by sending pulses of light through an optical fiber. The light forms an electromagnetic carrier wave that is modulated to carry information. Also, it enables high-speed data transmission, forming the backbone of modern telecommunications. An optical fiber is a dielectric waveguide that operates at optical frequencies. This fiber waveguide is normally cylindrical in form, and it confines electromagnetic energy in the form of light to within its surfaces and guides the light in a direction parallel to its axis. Now, history and evolution of optical fiber. Conceptual beginning. The idea of using light for communication traces back to the late 19th century with early experiments in guiding high light through bent glass rods. First optical fiber. In year 1970, growing glass work produced the first optical fiber with a loss of 20 dB per kilometer, which was a significant improvement over earlier attempts. Milestones in transmission. By the mid of 1970s, practical optical fiber cables capable of transmitting signals over long distances were developed and deployed. Deployment in telecommunication. Throughout the year 1980s, optical fiber technology matured and became the standard for telecommunication networks, replacing copper wires due to its superior quality and reliability. Advancement in transmission. The development of embryum-doped fiber amplifiers in the mid of year 1980s allowed for long-distance transmission without frequent signal generation, further boosting the efficiency of fiber optic networks. Widespread adoption. From the year 1990 onwards, fiber optic becomes important in global telecommunication networks, providing the backbone for internet infrastructure and high-speed data transmission. Continued technological advancement. Advances such as wavelength division multiplexing in the year 1990 and dense wavelength division multiplexing in the year 1990 dramatically increased the capacity of optical fiber system, allowing multiple channels of data to be transmitted simultaneously over a single fiber. Research and development. Ongoing research continues to improve fiber optic technology, including the development of new types of fibers such as dispersion shifted and non-zero dispersion shifted fibers and more efficient signal processing techniques. Basic optical laws involved in optical communication are: first is reflection. The law of reflection states that when a light ray incident upon a reflective surface at some incident angle phi 1 from an imaginary perpendicular normal, the ray will be reflected from the surface at some angle phi from normal, which is equal to the angle of incidence. Therefore, the angle of incidence phi 1 is equals to angle of reflection phi 2. Second law is law of refraction. Refraction occurs when light ray passes from one medium to another, that is, the light ray changes its direction of interface. Refraction occurs when density of medium changes. The refraction observed at air and water interface, air and glass interface. Next, refractive index. The amount of refraction and bending that occurs at the interface of two materials of different densities is usually expressed as refractive index of two materials. Refractive index is also known as index of refraction and it is denoted by small n. The refractive index is expressed as the ratio of velocity of light in free space to the velocity of light of the dielectric material. The refractive index for vacuum and air is 1.0 and for water it is 1.3. For glass, refractive index is 1.5. Snell's law. Snell's law states that the light ray reacts when it meets the interface of two media having different index of refraction. Phi 1 and phi 2 be the angles of incidence and angle of refraction respectively, then according to Snell's law, a relationship exists between the refractive index of both the materials, which is given as n1 sin phi 1 equals to n2 sin phi 2. The refracted wave will be towards the normal when the value of n1 is less than n2 and will be away from it when the value of n1 is greater than n2. This equation shows that the ratio of refractive index of two medium is inversely proportional to the refractive and incident angles. Critical angle. When the angle of incidence phi 1 is progressively increased, there will be progressive increase of refractive angle phi 2. At some condition, the refractive angle becomes 90 degree to the normal. When this happens, the reflected ray travels along the interface. The angle of incidence at the point at which the refractive angle becomes 90 degree is called critical angle and it is denoted by phi c. Hence, the critical angle is defined as the minimum angle of incidence at which the ray strikes the interface of two media and cause an angle of refraction equal to 90 degree. The actual value of critical angle is dependent upon the combination of materials present on each side of the boundary. Next important factor is numerical aperture. Numerical aperture is defined as n naught sin theta, where n naught is the refractive index of the medium outside the fiber and theta is the half angle of the maximum cone of light that can enter or exit the fiber, also known as the acceptance angle. Importance of numerical aperture. First is light gathering ability. A higher numerical aperture means the fiber can accept light at a larger angle, which is useful for capturing more light from a light source or coupling more light into the fiber. Next important factor is coupling efficiency. The numerical aperture affects the efficiency with which light from a source like a laser or LED can be coupled into the fiber. Mode propagation. In multimode fibers, the numerical aperture affects the number of modes that can propagate through the fiber. A higher numerical aperture allows more modes which can be beneficial depending on the application. Alignment tolerance. Fibers with a larger numerical aperture are less sensitive to alignment errors, making them easier to work with practical applications. Conditions to achieve total internal reflection. The phenomena of total internal reflection occurs at the interface between two dielectrics of different refractive indices only when the light is incident on the dielectric of lower index from the dielectric of higher index and the angle of incidence exceeds the critical angle. The principle of light propagation through a fiber. When a light ray is incident on the interface between two medium having different indices at an angle greater than the critical angle, then the light gets totally internally reflected within the medium of higher refractive index. Now, the structure of optical fiber. The optical fiber cable consists of four parts: core, cladding, buffer and jacket. The core of a fiber cable is a cylinder of a plastic that runs all among the fiber cable's length and offer protection by cladding. The diameter of the core depends on the application used. Due to internal reflection, the light traveling within the core reflects from the core and the cladding boundary. The core cross section needs to be a circular one for most of the application. Cladding is an outer optical material that protects the core. The main function of cladding is that it reflects the light back into the core. When light enters through the core into the cladding, it changes its angle and then reflects back to the core. The main function of buffer is to protect the fiber from damage and thousands of optical fibers arranged in hundreds of optical cables. These bundles are protected by the cable's outer covering that is known as jacket. Fiber optic cable jacket are available in different colors that can easily make us recognize the exact color of cable we are dealing with. The color yellow clearly signifies a single mode cable and orange color indicates multi-mode. Different types of fiber. Based on fiber used in communication, they are classified into 4 categories. First is step index fiber. It has a core with a uniform refractive index and a cladding with a lower refractive index. Light travels straight down the core, but different modes travel at different speed. The refractive index of core is higher than that of the cladding, but it suddenly changes at the core cladding interface. These fibers are classified into 2 types based on the number of modes they can transmit, and they can be single mode step index fibers and multi-mode step index fiber. These are less commonly used in modern application due to higher model dispersion. Second type of fiber optic is graded index fiber. Refractive index of the core decreases gradually from the center towards the outward, allows multiple modes of light to travel more efficiently than step index, reduces the modal dispersion, improving the bandwidth and performance. Graded index fibers are a type of optical fiber where the refractive index of the core gradually decreases from the center to the edge of the core. This gradual decrease in refractive index helps to reduce the modal dispersion, allowing for a faster and more efficient data transmission. The index profile is typically parabolic or near parabolic in shape. Graded index fiber have several advantages, including reduced modal dispersion, increased bandwidth, longer distance transmission, easier splicing. They are commonly used in local area networks, metropolitan area networks, data concept, high-speed internet connections. Graded index fiber offer a compromise between single mode and multi-mode fibers, providing a balance between bandwidth and distance capabilities. Third and the most important fiber is single mode fiber. Single mode fiber is a type of optical fiber that is designed to transmit a single beam of light over long distance. It has a small core diameter, typically 8 to 10 microns, and a higher bandwidth than multi-mode fiber, allowing for a faster data transmission rate and longer distance transmission without signal degradation. SMF is commonly used in telecommunication for long haul networks, internet backbone, and cable TV. Data centers for high speed data transfer between server and the storage system, metro networks for connecting buildings and campuses, access networks for the fiber to the home and fiber to the premises application. SMF has several benefits, including high bandwidth and faster data transfer rate, longer distance transmission without signal repeaters, lower attenuation and interface, smaller diameter and lighter weight. However, SMF also has some limitations, including more expensive than multimode fibers, requires precise alignment and splicing, not suitable for short distance application due to its higher cost and complexity. Fourth is multi-mode fibers. Multi-mode fibers is a type of optical fiber that can transmit multiple beams of light over short distance. It has larger core diameter, typically 50 to 100 microns, and a lower bandwidth than single mode fiber, but is more cost effective and easier to install. MMF is commonly used in local area network for connecting devices within a building or a campus. metropolitan area network for connecting buildings and campuses within a city, data centers for short distance data transfer between servers and storage system, industrial control system for monitoring and controlling industrial equipments, security systems for video surveillance and access control. MMF has several benefits including lower cost and easier installation, shorter distance transmission without signal repeaters, easier to splice and connect, support multiple signal transmission simultaneously. However, MMF has some limitation including lower bandwidth and lower data transfer rate. Shorter distance transmission, typically up to 10 kilometers, more susceptible to interference and signal degradation. There are two main types of MMF. First is step index, which has a constant refractive index in the core. Second is graded index, which has a gradually decreasing refractive index in the core, allowing the fast signal transmission. General overview of optical fiber communication system. Like all other communication system, the primary objective of optical fiber communication system also is to transfer the signal containing information like voice, data, videos, etc. from the source to the destination. The general block diagram of optical fiber communication system is shown in the figure. Now, the primary elements of optical fiber communication system, where the figure shows the major elements used in optical fiber communication system. As we can see, the transmitter stage consists of a light source and associated drive circuitry. Again, the receiver circuit includes photodetectors, signal amplifiers and signal restorer. So, let us discuss all the components involved in fiber optic communication system in detail. Optical transmitters. It converts the electrical signal into light signals. Optical transmitters are key components in optical fiber communication system that converts electrical signals carrying data into optical signals, which are then transmitted through optical fibers. These transmitters are essential for encoding and modulating information into light waves, ensuring the efficient and reliable transmission over long distances. Different types of optical transmitters. First is light emitting diode LED. LEDs are commonly used in short range optical communication system such as within buildings or for a local area networks. They emit light when current flows through them, producing incoherent light in the visible or near infrared spectrum. LED transmitters are simpler and less expensive than the laser based transmitters, but typically have lower bandwidth and transmission capabilities. Second type is semiconductor lasers. Semiconductor lasers such as fibre laser, distributed feedback lasers and vertical cavity surface emitting lasers are widely used in long distance optical communication systems. They emit coherent light with a narrow spectral width, allowing for higher data rates and longer transmission distance compared to LEDs. DFB lasers are particularly common in single mode fiber system due to their stability and precise wavelength control. Similarly, vertically cavity surface emitting lasers are favored in short range multi-mode fiber system and high speed data communication, that is in data centers. Next is optical receivers. It converts light signal back into the electrical signal. So, optical receivers are crucially important component in optical fiber communication system that converts incoming optical signal into electrical signals. These signal carries the encoded data transmitted through the optical fiber, enabling the extraction and processing of information at the receiving end of the communication link. Different types of optical receivers. First is photodetectors. This is often a photodiode such as a pin diode or avalanche photodiode that converts incoming optical signal into electrical currents. The photodetector's sensitivity and response time are crucial for determining the overall performance of the optical receiver. Amplifiers. After the photodetectors convert the optical signal to an electrical signal, the signal is usually weak and needs amplification. An amplifier boosts the signal strength to a level suitable for further processing. Signal processing circuitry. This includes circuits for noise reduction, signal filtration and equalization. These circuits help improve the quality of received signal by reducing the noise and compensating for signal distortion and losses that occurred during transmission. Clock recovery circuit. This extracts the timing information from the received signal, which is necessary for data synchronization. Decision circuit. This circuit determines the digital data, which is zeros and ones, from received analog signal. It usually involves comparing the signal to a threshold value to decide whether the signal represents a binary 1 or a 0. Demodulator. In a system using advanced modulation schemes, the optical receiver may also include a demodulator to convert the modulated signals back to their baseband form. Next is optical amplifiers. It boosts the strength of a light signals. Hence, optical amplifiers are critical important component in fiber optic communication system. They boost the strength of a optical signal without converting them to electrical signal, which helps maintain signal integrity over a long distance. Different types of optical amplifiers involved in optical communication. Erbium doped fiber amplifiers used a length of optical fiber doped with the rare earth element erbium. It pumps the laser at specific wavelength, usually 980 nanometer or 1480 nanometer, excite erbium ions in the fiber, which then amplify the light signal passing through the fiber at wavelength around 1550 nanometer, commonly used in telecommunication systems. Second is Raman amplifier. It utilizes the Raman scattering effect in optical fiber to amplify the signal. It pump laser injects into a wavelength shorter than the signal wavelength. The interaction between the pump light and the signal light amplifies the signal through the Raman scattering process. Wavelength division multiplexing. Wavelength division multiplexing is a technology used in fiber optic communications to combine multiple signals on a single optical fiber by using different wavelengths or color of laser light. This allows for the transmission of several data streams simultaneously over a single fiber, significantly increasing the capacity of communication system. This diagram helps illustrate how the wavelength division multiplexing technology enables the simultaneous transmission of multiple data stream over a single optical fiber, enhancing the overall capacity and efficiency of fiber optic communication systems. It has multiple lasers, each laser emitting a different wavelength. Similarly, it has multiplexer. It means combining the different wavelength into a single optical fiber. It has optical fiber also, the medium through which the combined signals are transmitted. Optical amplifiers placed among the fiber to boost the signal strength. Demultiplexer, which is used to separating the combined wavelength back into the original signals. Photodetectors or a receiver, which is used to detect the individual wavelength and converting them back into the electrical signals. Some benefits of optical communication system. Some of the innumerable benefits of optical fiber communication systems are immense bandwidth to utilize, total electrical isolation in the transmission medium, it has very low transmission loss, small size and lightweight, high speed security, immunity to interface and crosstalk, very low power consumption and wide scope of system expansion. Applications of optical fiber. First is communication system. The optical fiber communication system involves the transmission of information from the source to the destination in the form of pulses of infrared light signals. This communication method is suitable for long distance and short distance communication, allowing users to exchange various signals including voice, audio, video, data and telemetry signals. Elements of a fiber optic communication system includes transmitters, circuitry, light sources, photodetectors and receiver circuitry. Light emitting diodes or laser lights are preferred sources for transmitting signals in optical fiber communication. In contrast, p-n junction diode and avalanche diodes are the preferred photodetectors for reception and detection purposes. The optical fiber communication system is generally preferred over other modes of communication as it proves to be reliable and offers the minimum possibility of the input signal getting affected by electromagnetic interference. Also, the optical fiber based communication system has a significantly large bandwidth, fewer chances of signal degradation, provides high data security, is comparatively cost effective and consume lesser power. Next application is of medical equipments. Optical fibers are widely used in various medical equipments and research laboratory machines. For instance, the endoscope, otoscope, and encephaloscope, etc. are some diagnostic medical gadgets that rely on optical fibers for their general operation. Optical fibers are usually preferred for medical diagnostic and treatment applications because they offer no or minimum side effects and harmful consequences, are flexible, have a significantly less surface area and do not emit toxic radiation. Other than diagnostic and treatment application, optical fibers can also be used for research application in the field of microbiology and biomedical sector. Next application is of internet. Internet is one of the prominent examples of real life application that makes use of optical fibers. Optical fibers can transmit a large amount of data from one place to another in relatively less time. The high data transmission speed, flexibility, lightweight nature and ability to easily carry bulk data makes optical fibers suitable for internet cables in place of traditional copper wires. Automotive industry. The automotive industry uses optical fibers to illuminate the interiors of vehicles. This is because optical fibers do not consume much space, radiate bright light, can be deployed flexibly in the mechanical structure of the car, are economical, do not consume much power, have minimum chances of signal deterioration and leakage, have a significantly longer lifespan and do not require frequent maintenance. Beside interior illumination application, the automotive industry may also employ optical fiber in the exterior lamps of a vehicle. Also, optical fibers can be used in a system for communication purposes. For instance, in case of an accident, the network of optical fiber can be used to transmit the signal generated by the collision detector or sensors to the internal circuitry of the vehicle and help quickly activate the traction control and airbag system. Using optical fiber for communication among different parts of a vehicle is advantageous in the optical signal travel at the speed of light, thereby improving the response time of the control system. Next application is of telephone. The local telephonic connectivity within the building, the city or the country, and the global telephonic connectivity among users in different countries typically rely on the primary working principle of optical fibers. The optical fiber cables are bundled together for cellular communication and laid underground or beneath the sea surface area. This increases the security of the signal as the flowing data is less susceptible to electromagnetic interference introduced by other electromagnetic waves in the environment. Next and most important application is military application. Data transmitted with the help of fiber optics is highly secure and only authenticated users can access it. Since the main focus of military application is data security and privacy, this unique property of optical fiber can be exploited in many military applications. All three military applications, namely Army, Navy and Aerospace, use optical fibers to establish a shared channel between the station to exchange information and analyze data. Some prominent application of optical fiber in the field of military include avionics and mission control system, high-speed mission data exchange, flight planning, sensor data fusion, controlling the operation of weapon systems, etc. Space application. Some space applications such as satellite communication, remote sensing, high power laser system, multispectral and hyperspectral imaging, optical data communication, LiDAR, atmospheric monitoring and analysis, etc. rely on optical fibers for their operation. This is because optical fiber minimizes the risk of interference, allows maximum bandwidth and makes the system cost effective, flexible, simple and lightweight. Different challenges involved in fiber optic communication. First challenge is installation cost, as it has higher installation cost due to specialized equipment and skilled labor requirement is required. Fragility requires careful handling and protection against bending and physical damage. Upgrades and maintenance. Upgrading equipments and expanding capacity can be complex and costly. Conclusion: though there are some negatives of optical fiber communication system in terms of fragility, splicing, coupling setup, expenses, etc., but it is an unavoidable fact that optical fiber has revolutionized the field of communication. As soon as computer will be capable of processing optical signals, the total arena of communication will be opticalized immediately.